Alright, in this video I want to take a look at the properties of definite integrals. Start with this one. The integral from b to a of f of x dx is equal to minus the integral from a to b of f of x dx. As if you swap the order of integration, you just change the sign. Essentially, what's happening here is that this is the way we normally think of, if b is bigger than a, so you're going from the smaller endpoint to the bigger endpoint, that the delta x, oops, upside down delta, that the delta x that you calculate for this one is the b minus a over n, and then of course n heads to infinity. But on this one, the delta x that you're calculating is a minus b over n. So you get the same height function in both places, f of x, but because you're integrating one of them backwards, you're actually using a negative delta x. So the result just becomes the opposite. So if this one is positive, this one will be negative, or vice versa. Okay, so there's property number one that we want. Property number two, this perhaps is self-evident, that the integral from a to a of f of x dx is equal to 0. I see this two different ways. The picture, excuse me, the picture is, here's my function, y equals f of x, and I'm going to integrate starting at a and ending at a, and I'm looking at the area underneath the graph over that point. Well, the width is 0, and so I don't care how tall it is, the area is 0. Another reason that I see this is that if property number one is true, then if I reverse the order, instead of going from a to a, I go from, well, a to a, then it should change the sign of the result, and the only number that when you change its sign gives you the same number back again, well, the only number that does that is 0. So anyway, this has to be 0. 3. How about the integral from a to b of a constant function dx? Well, the picture of that, of course, looks like there's your x-axis, there's your y-axis, here's a, here's b, some constant c. Well, if you're integrating a constant function and you're looking at the area underneath the function over the x-axis between a and b, well, that's just a rectangle. And so you look at the area as c times the quantity b minus a. That's just length times width, or width times height, or length times height, however you want to think of it. One dimension times the other dimension. So that one's pretty easy. This one is not quite as easy to see, but I think it's still pretty agreeable for most people. That if you take the integral of a sum of two functions, that's equal to the integral of the first function dx plus the integral of the second function. Now, if you think about how you add functions, I'll draw a picture here. If I've got like the line y equals x, and I've got the line y equals sine x, right? That was kind of funny looking. Let's try that one more time. One more time. There we go. So if you add those two together, and I'll add them in purple here, if I can find purple, maybe that's purple, I don't know. Essentially, for each x value, you're looking at both y values, so the blue curve, the red curve, add them up. So I'm essentially going to just put that sine curve on top of the line. I mean, for each value of x, I look at this height here and this height here, and I stack them on top of each other to get the total height. Well, if I now look at the area underneath the total thing, I'm saying that's the same as the area underneath one of them plus the area underneath the other, because you've taken all this area underneath this one and stuck it up on top of that one. Right? That's that property right there, that the definite integral of a sum of two functions is the sum of the two definite integrals. Back to blue. 5. The integral from a to b of a constant times a function is the constant times the integral of the function. There's a lot of different ways to see this. One is thinking back to the definition, that how do you actually calculate these things? Well, you're going to cut the interval from a to b up into n pieces. For each piece, you're going to plug in a function value. You're going to plug in an x value to get a function value for the height, and then multiply by delta x. Well, the thing is, every one of those heights is going to be some f of x times c. So when you add them up, you've got a whole bunch of things added up that each have a factor of c in it. So use the distributive property and factor the c out. That's what's happened here. Essentially, we're saying you can add up the functions, those little areas, without multiplying by c, and then multiply by c at the end, or you can multiply by c to begin with for all those height functions and add up all the areas. The other way I see this is the effect of taking like y equals sine x and y equals 3 sine x. That's more like 2 sine x, so let's say sine x and 2 sine x, that multiplying a function by a constant takes all the y values and multiplies them by 2. So everything is now twice as tall as it used to be down here. So if you're looking at the area underneath, this area versus that area, you haven't changed anything in the x direction. Everything's just as wide as it used to be, but everything's twice as tall now. So you're getting twice as much area. Right? So if everything's as c times as tall, then you're getting c times whatever the area was. These two properties, by the way, properties 4 and 5, if I can get them both on the screen at the same time, the fact that essentially the integral distributes over addition, right? It's almost like a distributive property here, where you got it into this one and to that one with the plus sign in the middle. It's not really a distributive property, but it's called a linearity property. And this one, where the integral of a constant times the function is a constant times the integral, anything that satisfies both of those two properties is what's called a linear operator. An operator is a function on functions, right? Functions take numbers in and give you numbers out. Operators take functions in and give you functions or numbers out. Numbers are just constant functions. So this definite integral operator is taking a function in and giving you a number out, so the area underneath the function. And it turns out it satisfies these two properties, and it's what's called a linear function. If you ever find yourself interested in linear things, take a class on linear algebra, and we'll talk about linear operators. Anyway, number 5. Number 6. Property number 6 here. Yes. 6 is somehow somewhat similar to 4, but somewhat different as well. Look at the integral from a to b of a function. And I want to break it up, but I want to break it up in terms of the interval. So let me draw the picture down here. The idea is if I've got my function from a to b, and I'm looking at the integral, so I'm trying to find the area underneath there, and I throw in a point c in the middle here, and I can look at this integral from here to there, and then this integral from here to there, and the sum should be the totals, and that's the way it works. So the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Notice that in property 4, you're breaking up the function. The interval, you're going from A to B, A to B, A to B. All of those are the same, but it's the function that's getting broken up. F plus G, F by itself, G by itself. In number 6, the function is staying the same, but you're changing the intervals. This side is all the way from A to B, and this side is, two of them, A to C, and then C to B. One thing I point out here is that property, what did we list it as? Property number 2 is important because in some ways, when you integrate from A to C and then integrate from C to B, you've actually counted that strip right there twice. And you don't want to overcount the area, but it turns out that the amount of area that you've overcounted is equal to 0, so it doesn't matter that you've counted it twice. Also, this picture works, or this formula works, even if the C is not in between A and B. Because notice if you had something that looked like this, where here's A and here's B and here's C, and you got your function, right? So you're looking for the integral from A to B. You're looking for this thing. But this says, no, integrate all the way from A to C. So start from here, head all the way out to there, right? Stop at C, but then integrate from C to B. Well, C to B is coming backwards, so you're integrating back over this. So you A to C gets all the area from A all the way up to C, but then you're subtracting off from C to B, which gives you just the A to B part. Okay. Likewise, if you started off in the other direction, if it looked like this, where C is over here, and then A, and then B, you're looking for this area, but you start by going this way. Well, you're working backwards, so you're calculating negative area, and then you go from C all the way back to B, you're getting all that back again, and then you're getting all this again, and it's just A to B. So, although I think of this mainly with C in between A and B, and that you break the interval up into 2 pieces to integrate over each piece. C doesn't actually have to be in between to keep this property true. Okay. When would we want to do something like this? Well, quite often if the function is a piecewise function, so you have one description for the function in one interval and another description in another interval, then it might be convenient to say, well, let me just integrate over this one interval where I have this description of the function, and then let me integrate over the other interval where I got the other description of the function. So that's the main place where I see people breaking it up like this.